Good day. This is the video of solutions for problem set 8 for Kevin Ahern's BB450 at Oregon State University. You can see the problems on the screen, and I'll be going through and solving these. The first problem asks students to predict the cutting site of a serine protease that had the following alterations to its S1 pocket. First, we see, what if it had arginine at the bottom? To answer this problem, one must remember a little bit about what the S1 pocket of a serine protease does. The S1 pocket is the place where the side chain of an amino acid binds that's immediately adjacent to the cut site for the enzyme. So the S1 pocket is a positioning device for the enzyme's specificity. If we look at the S1 pocket and we draw it in this fashion, where we have at the very bottom an arginine, as was described in the problem, we would see that the side chain of arginine would have a positive charge at physiological pH. That would mean that only amino acids that had side chains that were negatively charged at physiological pH would fit into this S1 pocket. This would mean that the only amino acids that would fit into the pocket under this condition would be aspartic acid, which is negatively charged at physiological pH, glutamic acid, which is also negatively charged at physiological pH, and possibly cysteine. Cysteine has a side chain of a sulfhydryl group that has a pKa value of about 8. So some of those side chains of cysteine would be negatively charged at physiological pH. The second part of the problem asks, what if the S1 pocket had a glutamate at the bottom? Well, we remember, of course, that glutamate has a carboxyl side chain that ionizes at physiological pH. So if we had glutamate at the bottom, it would have a structure that looks something like this. A negatively charged ion at the bottom, of course, would attract a positively charged side chain of an amino acid. And the amino acids that would have this characteristic at physiological pH would include lysine, which has an amine side chain that's positively charged, arginine, that also has an amine side chain that's positively charged, and finally, histidine. Histidine has a pKa value of about 6, so at least some of the side chains of histidine would, in fact, be positively charged, although not nearly as many as lysine or arginines, each of which have pKa values of 10 or greater. The third problem asks, what if you had a S1 pocket with a tiny pocket with no charge to bind? And if we had that, we would draw this schematically as a fairly narrow side chain looking like this. We had the S1 pocket looking something like this. And if this were the case, the only side chains that would fit into that S1 pocket would be those of amino acids that had fairly small nonpolar R groups. This would include, for example, glycine, which has only a hydrogen. It would include alanine. And it would probably include things like leucine, isoleucine, and valine, depending upon, of course, the exact configuration of that S1 pocket. The last part of the problem asks, what if we had a large pocket with no charge? Well, when we think of the pockets, we always think about how well things will fit in there. And in this case, I've drawn the S1 pocket a little bit larger than the others. And for this, we would predict that only those amino acids that had large, relatively nonpolar side chains would fit into the S1 pocket. This would include, of course, phenylalanine, which has a benzene ring. It would also include tryptophan, which has a fairly large nonpolar side chain. It could also include tyrosine, although tyrosine does have a hydroxyl group that might give it a little bit of polarity. The second problem says that you discover an unusual protease. At the bottom of its S1 pocket is located a cysteine. And so when you try to use it to cut any protein, it exhibits no activity whatsoever. What is the most likely reason? Well, when we think about a problem like this, we think about, first of all, the fact that we have an S1 pocket, and now we have a sulfhydryl sitting at the bottom. We remember that sulfhydryl groups are fairly reactive, and so that any protein that had a cysteine with a sulfhydryl group that came into here, where we had the rest of the protein up here designated by the R, these two cysteines would be reactive towards each other. And if that happened, a covalent bond between the two would form a disulfide bond. And that disulfide bond would not be broken by any part of the process. So that in essence, this enzyme would react once. It would not break any peptide bonds, and in fact would only interact with and form a disulfide bond with any protein that bound to it. Consequently, the enzyme would have no activity because it wouldn't be able to proceed through the process of breaking a peptide bond. Problem 3 says, based on what you've learned in class, will a metalloprotease have a fast and a slow step to its catalysis? Why or why not? Well, a metalloprotease, we have to remember, is a protease that uses a metal ion within its structure to hold onto the water molecule in its active site. That water molecule gets a proton pulled off of it, and that creates a nucleophile that attacks the peptide bond of the bound peptide that comes in. Now, if we had such a situation, we would have the water molecule, or the ionized water molecule, that would, in fact, be causing the catalysis. That's a little bit different than we had with the serine protease. With the serine protease, we had a nucleophilic alkoxide ion, and that nucleophilic alkoxide ion attacked the peptide bond. It released one part in the fast step of the process, but in the slow step of the process, that covalent bond between the oxygen of the serine and the attached peptide had to be broken. And that breaking of that bond was what caused the reaction to be slow. The difference between a metalloprotease and the serine protease, of course, is that the serine protease does not have any intermediate in which the peptide becomes covalently bound to the protein. It will become bound to the oxygen of the hydroxyl, but that oxygen of the hydroxyl is not attached to anything. So in the case of the metalloprotease, you would predict that it would not have a fast step and a slow step to its catalytic process. Problem 4 says, as described in class, mutation of any of the amino acids in the catalytic triad of a serine protease resulted in a drastic reduction of its activity. Predict other amino acid substitutions for catalytic triad amino acids that would have the least effect on the enzyme's activity. Well, let's review, first of all, the catalytic triad of serine proteases. That includes a serine that had a hydroxyl group. That includes a histidine that had this 5-membered ring. And it included aspartic acid that had a negatively charged carboxyl group, something like this. Well, when we look at this, we think about other amino acids that would have similar side chain structures. And we immediately see, first of all, serine has a partner in threonine. And threonine is very much like serine, except for it has an extra carbon in it, as I've drawn here. And we also remember that aspartic acid is very much like glutamic acid, which has an extra carbon in it, very much like this. Now, we would predict, based on this, that these substitutions of amino acids, as shown here, would have most likely the least impact on the catalytic activity of the enzyme, because it would be preserving the chemistry of the individual groups that are on this protease. Now, of course, whether or not that would actually occur depends, of course, upon the three-dimensional configuration of the active site. So it's not a simple matter, but based on the problem and the predictions that one would make, you would predict that the threonine and the glutamic acid would likely have the least impact on the catalytic activity of a serine protease. A histidine, by contrast, has no real partner that can exhibit similar chemistry. Histidine has a pKa value of 6, and that pKa value is close to physiological pH. None of the other amine-containing amino acid side chains, amino acids that have side chains, such as lysine or arginine, have a pKa value anywhere near that area, because lysine and arginine both have side chains with pKa values from up to 10 to 12 pKa values. Problem number 5 says, describe how you might incorporate a catalytic triad into a carbonic anhydrase to engineer a new enzyme that might be more active at a lower pH. And then the question says, how would it work? Well, we remember that the carbonic anhydrase, first of all, was catalyzing the solubilization of carbon dioxide in water. And that made carbonic acid, which, of course, ionized to form bicarbonate plus a proton. Now, in the catalytic mechanism of the carbonic anhydrase, we remember that there was a necessary step in which the water that was present in the active site had to be ionized. And the ionization of that water was necessary for the carbonic anhydrase to perform its function. So I'm asking in the problem to think about how you might incorporate a catalytic triad to engineer an enzyme to perform a function like the carbonic anhydrase in the unmutated form. Well, this is a little bit of a tricky problem, but and again, it's a speculation kind of problem. So we think about back to the catalytic triad where we have the serine hydroxyl group. We think of the histidine ring. And we think of the aspartic acid side chain, looking something like that. The nature of the catalytic triad of this serine protease was such that this overall process resulted in the ionization of this serine side chain to make this alkoxide ion. So this proton would go away. Well, if we think about the parallel in the carbonic anhydrase was the limiting step in the ionization of the water was the loss of this proton, and that required a high pH. Its ideal activity was at pH 9 because at a higher pH, protons more readily come off of water. Well, how might we engineer this so that we could pull a proton off of this with a catalytic triad? What if we engineered a carbonic anhydrase such that we had a structure like this where we actually had a water that was positioned something like this? We could, in fact, have this guy be pulled by the histidine, and when it's pulled by the histidine, we're left behind with a reactive hydroxyl that would then attack the carbon dioxide molecule and create carbonic acid. Now, it's just an exercise in thought and not something that would necessarily be very easy to do. But that's how I would envision engineering such an enzyme.